Yeah, hello everyone. Thank you for tuning in. I'm Aravind Sankaran from Jülich Supercomputing Centre in Germany. I work with the application optimization and user support team here with Dr. Wolfgang Frings, and I'm currently involved in developing tools and providing user support and training. I'm also a PhD student at RWTH Aachen University since 2020, and my supervisor is Professor Paolo Biantinesi. He's currently in Umeå University in Sweden. He's also director of the HPC 2N Supercomputer Center there. Mm, So the focus of my topic, the PhD topic, is mostly related to performance analysis and benchmarking. Yeah, so that's about me. Second. Yeah. So in today's talk, so there are going to be two parts. First, I'm going to talk a bit about application benchmarks, which sets the context for this talk, and then present a specific graph-based methodology for benchmarking applications. Then I will demonstrate some applications of this benchmarking methodology with IO traces from IO system call traces, and then show you some demo. The work with this methodology actually started during my PhD, so I think it's worth going into a bit of the history so that there's some context to this. So it all started when we started looking into the linear algebra mapping problem. That is, any high-level expression can be mapped onto a sequence of optimized low-level calls. So the HPC community has spent significant effort in encapsulating these calls into BLAS and LAPEC libraries, and these high-level expressions can be mapped into sequence of these low-level calls. However, using these set kernels are not so straightforward because there could be more than one way to map the high-level expression into the set of low-level calls. So just to give you some perspective, um, let me consider this high-level expression, which commonly occurs in image recognition problems. So as a mathematician, one might write this expression as shown in the screen. So, but if you give the same expression as input to MATLAB or any high-level language, it's gonna proceed as follows. First, it computes a matrix vector product, followed by the matrix multiplication with the gem kernel, and then xpi, and then so on and so forth. So that's a sequence of high-level calls. Right? So the most expensive operation here is the matrix multiplication. So that's one variant. So if you manipulate this expression a little bit, like you take the x inside, then you see hx is one matrix vector product. It's a BLAS1 call with GEMB, and then if you proceed with the sequence, you completely eliminate the matrix multiplication. So then if you compare the execution time of these two variants, they both compute the same expression mathematically, but the second variant is an order of magnitude faster than the first variant. So the bottom line is an expression can have many different, sometimes even hundreds of possible sequence of linear algebra calls. And then one has to identify the optimal sequence. So, but why is this a problem? Maybe if this was 1 decade before, we might think, okay, if one is coding for HPC, they should be aware of all this. But today the story is a bit different because there are a lot of high-level languages which is wrapping up so many things from the user. And then we are finally asked to trust the languages to do the mapping. So in the end, we have high-level languages, for example, TensorFlow, PyTorch, Eigen, MATLAB, so on and so forth. And now the question lies, okay, do these languages do the mapping in the way it should? Like, are they doing something stupid, or are we good enough to trust them? And because of all the abstractions, we are kind of reaching a dangerous phase where the user, if you're going to ask, you might not be surprised if you hear, okay, I'm just using PyTorch, or more worse, I'm using transformers, which is one level above PyTorch, and the mathematics is lost. And being in user support, if the user is not giving enough information, you have to rely on other sources and documentation. And the worst thing that you want to do is to look into the code and then spend weeks going through the documentation. So to address this issue, a part of my work during my PhD was to develop some benchmark to evaluate the build of the frameworks, um, in a sense, to evaluate the build and prepare a report, which kind of gives us a platform or a set of numbers to do some audit. So for example, here you see a report for PyTorch for a specific version and built on a tool chain. So what you see here, 2.1.2 Commodore hyphen FOSS is an easy build code. So just by, and since many HPC sites use easy build, looking at this code, you can immediately decide, okay, this is PyTorch built on OpenMPI with OpenBLAS toolchain and built on this site. So as soon as one builds, in addition to the usual test, the design was to also run these reports, run these benchmarks so that we get these reports. So what would be in these reports? For example, there are multiple things. I'll just quickly walk through it. And first we checked, okay, do they use the optimized call? So if you want to do a matrix multiplication, these are the APIs, and are these are they equivalent to the optimized call if you would do it with C? And if they are close enough, it's okay. And then we check a lot of other optimizations like common elimination. For example, here you see two expressions which have the same common sub-expression. So if you give this as input, is your framework computing the matrix multiplication twice, or is it just once? So here for one matrix multiplication of size 3000 cross 3000 plus 0.5 seconds. So this should not be twice as much. Otherwise, it's doing redundant work. So here it doesn't. And then we check more patterns, like when you repeat the common sub-expression and multiplication, do they parse? And here they don't. So for an expression, for example, you take E2, you give this expression A transpose B and A transpose B, and you don't give a parenthesization, you see it fails, like it makes a redundant computation. So the idea, maybe I would show, second. Yeah. So how this would look like is that these reports are generated along with the compilation. It's designed to be generated along with the compilation, and you have these numbers where we test so many different things. And then in the end, you get a score. So this is done for many other frameworks as well. For example, I also compare JAX and TensorFlow, and then you see certain things are not the same. So JAX, for example, cannot identify common sub-expression in multiplication. And we also checked matrix chains. For example, what are the APIs each libraries have for different operations. So the idea is to have these kind of reports, and the purpose of these reports is, on one hand, it serves as a guide for the users to know which APIs are there and what the language is capable of, and then also for supporters to serve as a guide to audit codes that use these frameworks. And since many users are using the ML frameworks, such reports could be valuable. So at the moment, the version is the this benchmark is what I call lab linear algebra aware benchmarks. And the current version is 2022, and 2025 we have planned to release this with the continuous benchmarking integrated, and it's yet to be released. And more information about this can be found in this paper that you see at the bottom. So why am I talking about this? Because here I wanted to bring the context of application benchmarking, because now with this application benchmark, we get some flexibility to have users build and design benchmarks and compare the performance. So then we started applying this to for optimizing to perform algorithmic optimization. And in these cases, it's more or less common that users have one or more configurations, for example, of the same application. For example, you have different, sorry. you have the same code but different configuration options, and then you have some kind of trace information for this, and then you want to explain the difference in performance based on the trace. For example, here I show you 10 variants to compute the generalized least square problem. They all compute the same expression mathematically, but you can see they all differ in performance. Some of them differ in performance. And what I wanted to answer was, okay, what is that? So one thing, there are two challenges here. Based on these measurements, you classify them into performance classes and then try to explain the difference between these classes in terms of the traces that you see here. So to this, I first used the DFG, the directly follows graph method, to do this. And this, for example, here you see on the right, you see the algorithms and their variants. And the nodes of these graphs are each unique element in the trace. So here in this case, they are the blast calls, right? And an edge indicates that one call follows another. So if there's an edge from transpose to port RF, it means that transpose precedes port RF. So here you see in the 10 algorithms, it starts either with port RF or transpose. So there's a start symbol, and then it goes to either transpose or the LU factorization. So that's the kernel for this. And then you so on and so forth. And then now I use the coloring scheme to explain the difference between the two algorithms in the algorithms in the two sets to see, okay, are the algorithms in set 0 doing something different than algorithms in the set 1? So here the green nodes and edges indicate those kernels and edge calls, kernels and sequences that occur exclusively in the set 1, and red are those that occur exclusively in set 2. So with this, you see, okay, the badly performing algorithm are doing solving a linear system using QR factorization. So what was good about this DFG was that it was able to concise the information from a trace into a representation, which was important for the benchmark reports. So holding this thought, now the picture is still incomplete without, I haven't talked about IO yet. So the picture is incomplete without IO. Now, let's hold this idea about application benchmarks and the DFG a little bit, and now talk about IOs. And then I will bring back how I can append the IO information into the lab reports, which is the linear algebra web benchmarks. So to this, I need data of the IO traces, but where do I get them? So to this, let me first briefly walk you through the IO stack. So any parallel application would issue IO requests to the high-level libraries or system libraries like libc, stdio, and then these libraries in turn issue calls to the operating system, and then operating system first checks if it's a read or write call. It first checks if the data is there in the virtual memory. If not, it issues a request to the file system, or the data can also come from the interconnect. So even if you're using InfiniBand, the operating system should touch the device file somehow. All right, so of course, one could use the traces on a higher level, like traces from MPI IO or HDFI layer, but at that point, you have to keep track of the versions of these APIs. If they update, if the version changes, then you have to make sure they are updated. So for the moment, I do not consider the traces from high-level APIs. So I'm going to stick to those from the operating system because they are much more standardized. And also, you can also use the traces from a lower level, like from InfiniBand traces, but then sometimes you need permissions from admins to get those traces. So it's safe to use the traces from the OS for the moment. And this you can do by there's this nice Linux utility called STrace, which works on any arbitrary command, Python, Fortran, or even if your code is inside a container, you just prefix your command with STrace and you get the sequence of system calls here. So this would be my source of data. And of course, you can prefix STrace with options to get more information. So here I'm going to focus only on read and write, and also variants of read and write like pread 64, read v, and so on. So what information I need is the process ID, the timestamp for each entry, and the name of the system call, the file path, the number of bytes requested and the number of bytes returned, and duration. So you get all this from the STrace logs. What STrace does is it could generate one trace file per process, but at the moment I generate one trace file per node, and with the PID you can differentiate the traces from each process. So it's gonna generate a lot of data. So if it's a HPC application running on a large number of nodes, this is gonna be a large amount of data, and the challenge is how do you extract useful information from such a data? So the idea is, so let me call each line of this log as an event. So the idea is to map each event to a string called activity, which helps you answer certain questions. So this activity is like a way for you to navigate or search query through this event log. So for example, here, let me say, okay, I map every event to a named entity called activity, which concatenates the name of the system call and the first two levels of this file path. So because with the first two levels, I can infer the file system on which this IO was performed. Right. So this way, then for each activity, there could be multiple events, and then so this is like an partial map, which means not every event needs to be mapped to an activity. Some can return none. So what you're doing two things here. On one hand, you're filtering the event log, and on the other hand, you're using this mapping function to focus on specific parts of the event log. So the event file is what I call event log, and then this structure can be used to with this structure you can use some of the existing techniques to build the directly follows graph, which I showed you before. So this is the overall idea. So how would this work? So let's say you have a trace log from two process P1 and P2, and then you use the timestamp to arrange the order of the activities. And if these are the two activities, I would just go on logs one by one, or yeah. So first the activity, the process 0 starts with activity read software. So there is an edge from start to read software, and then I update the index by one, the number by one. And then read software follows read software, so there is a sales loop. So again, another one here, and then read software to write project, and so on and so forth. Then when I append the second process, I add information to the same graph. So now again, another activity starts with read software. So I update this edge number by another. So there is two, and then read software follows read project, which creates a new node, and then I update the numbers, and so on and so forth. So this technique rather simple, but it gives me a way to concise a lot of information in the event log into this nice graph, which presents a summary of what's happening, which gives me a footprint of what's happening under the hood. So yeah, so that's the whole idea. Let me show you some demo of how I'm using this information to append in the lab reports. Okay, yeah. So I considered a, a, a vision transformer model, VITB16 from PyTorch. So the code is rather simple. So most of the things are abstracted here. So this is a transformer model for image recognition. And here the user uses the transformer package to just import the model, the machine learning model. So there is nothing much you know from this. So you're just uploading the model, reading the images, and then using this variable to just classify them. So the code is simple. So this code is run on two nodes, on each node on 18 cores, so 18 CPU cores and one GPU. So I haven't So I'm just using the code as suggests. So 18 CPU cores and 1 GPU on 2 nodes. So it's running concurrently. So the first thing is that since most of the things are abstracted, I want to know, okay, what libraries are being loaded under the hood. To answer this, I create a mapping function which maps each event and sees if there is a word called .so something. And then I map it to an activity, build the event log, and then get this graph. And then this is what I get. So here you see it's 18 plus 1 GPU 19 into 2 38 times. So one thing that I immediately see here is that this event, this library was loaded concurrently by all the process. So one thing I could say is that they are not using MPI or OpenMP. So it's concurrent. So it's concurrent process and each process is loading these libraries. And if you see, so the red lines here are the IO events on this graph. So on the timeline. So if I can, yeah, 1 second. So you see here, 45, almost 45 seconds has been taken just to start the process here, right? So this kind of information I get to know even if the code is inside a container. And then I see, okay, for each library, how much data has been loaded. And here load is the relative time spent for each activity, in relation to other activities. So if I see here, yeah, okay. The time taken to load this library has been a little bit more than compared to other libraries. And then this data structure, I can use it to compare with libraries loaded at other sites, maybe with other settings. So because this DFG then gives me a way to compare, okay, I load these libraries, maybe the performance is less, and then I have another build of the same software, but it's giving a better performance. Then I have these two graphs, merge them, and then see what's being happening. Yeah, so again, here in this graph, what you also see is the performance numbers. So each dot here, so the blue dots are the efficiency of each CPU core. Because since this is a user code, since it's a machine learning model, I know it's VIT, so I know the number of flops it is computing. So here, to process each image, the input size is 224 cross 224 cross 3, so that I know how many bytes are the input, and I know how many flops, so 17 gigaflops. So when I time this and then divide this flops by the elapsed time, I get the performance. So for CPU, it was around 29.61 gigaflops per second, and for GPUs, it was like way more, like 1,700 or 1.7 teraflops. And this I compare with the performance that is achieved when you do a matrix multiplication, that is SGEM. So the lab, what it does is has some reference benchmark for each system. And for this system, this was run on Jülich Booster, and on Jülich Booster, when you do SGEM on a CPU core, it achieved around 99 gigaflops per second for single procession, and around 19 teraf 9. Oh, sorry, this is yeah, 19,000 gigaflops. So yeah, so that's almost this is chat gigaflops per second, right? So this was way more. So what you achieve on the GPU is almost 0.05% of what could be achieved. But again, we are not trying to achieve the best performance here, right? So we needed some reference number. Okay, so now I have the libraries. What about the IO? So I do the same thing, but map them to the read and write calls on different file systems, for example, home, project, and the devshmem, which is the shared memory. Um, the model size is so okay. Well, something is being read from home. So this is probably the model. So this is the model. So the model size of VIT B16 is around 300 megabytes. But what you see here is 2.26. So what's happening here is that so here I only show read and write, but you could also do an mmap. So what would also it's also possible that mmap is used to load the library. So here when you look at the raw logs, you see it first reads some metadata of the model and then directly loads the model to memory with mmap. So you can append this graph with such kind of events. So here the model is loaded, and then here you see most of the I/O happens um, uh, and when reading the images from this project. So this is really data hungry. The GPUs are data hungry. So here in this model, the batch size for the CPU is one, but for GPU, the batch size is 228. So it needs 228 images. It needs to read 228 images before performing one computation. So this is really keeping the CPUs idle. All right. But so yeah. So you see the idea here is the speed at which you get the data. But what can you do here? So what happens if you move the data to DevShmem? So instead of reading from project, is file system a bottleneck here? So we tried this, but when we tried the same thing by just instead of having the data in project, we moved it to DevShmem. But then you see here the performance improvement is not so much. So from 1700 you went up to 1800, but then the performance improvement is not so much. But why? If you notice, you see the number of read operations with with project it was around is 97,000, but here it's way more. The problem here is that the block size of the project file system is around, so for each operation, you get 4 megabytes of data. But when you do the same thing with DevShmem, the block size is 64 kilobytes. So now the OS is becoming too much busy. So it's having to handle too many calls. So now this is also becoming a bottleneck. So because of this, there's not much performance gain. And then what we tried to do was yeah, so here in this code, so the IO is happening asynchronously, but there's just one thread working on IO. So we try to increase the number of threads, and then keeping the images in the project. But now you see there is some improvement in performance. Yeah, so now the GPUs are doing a bit better. At least, so now we have 5 threads working simultaneously to get the images, and now you see immediately see a jump in performance, you see a jump in throughput. So the bottom line, what we learned here was the file system was not a bottleneck. Our systems can handle 50 gigabytes per second. So the file system was not a bottleneck here. And this code is actually compute intensive. So if you see 17 gigaflops for just a small image, so that the input intensity is really high. So this is in a way a power hungry code. So to test this, we ran this for yeah, so without any IO, just fake images generated within the memory, and you see the GPUs can get can go to around 8 teraflops per second, and this is like almost 50% of the peak benchmark, and that's okay. GEM is an truly optimized code. You don't want to, you really can't get that much performance, but that's okay. And just for the sake of clarity, I also ran this code on another site, which is on HPC2N. So in Jewel's Booster, we have A100, so the peak is 19 teraflops per second. And we also have H100 nodes on Jupyter, which is not yet in production. So I ran this code on HPC2N, where they have H100 in production with the file system that's there up and running. So here for H100, the peak performance I got was around 52 teraflops. And here again, yeah. So the performance was almost twice than what I got with A100. So these are kind of simple analysis what I could do with this tool. And what you see here is, I get back to the presentation. These reports are mostly static HTML code. So once you get, so the actual data size was around 400 megabytes. And then after compiling all this, you get a report which is less than 15 megabytes. And these are static HTML report, meaning the user can download it and then read this without having access to the internet. Yeah. So what's behind all this is a tool which builds this TFG, which is called STrace Inspector. And this at the moment generates one log file per node used. And then the parsing of log file and mapping them into activities are all done in parallel. So there is one process working in parallel. So I assume that I could use a whole node. So we have a beast in front of us, like we have 48 cores, 288 cores. And so we won't use all of them. So I try to maximize as much as possible. And then this processing happens in a matter of few seconds. So the bottleneck happens when you have a lot of activity. So ideally, you have to design a mapping function in which, for all intents and purposes, the number of activities should not be too much. So if it is too much, then you have a lot of nodes in the graph, and it's going to be very hard to navigate through the whole node. So a part of the thing is also, at the moment, I do not allow users to have their own activities. So I define the activities so that the number of activities is short. So as long as that is true, the complexity of constructing the DFG is not so much. So again, this is a fraction of a second. And the source code is available online, but the new version, which I think I will release in the next couple of months, will also have trace the map calls and have a lot of other features. So yeah, we also have a paper on showing some applications of this tool. So what this tool does is it gives you a simple data structure of this DFG, and what one could do is take this data structure and have and then render it in the way they want it. So here I appended this information to the lab report, but you could also do something else with this. So that is all from my side. So the main point to take away from this talk is that the DFG-based synthesis methodology to process a lot of traces into a representation, which is going to support you in generating reports that will in turn support in performance audits and optimization. Thank you for your attention, and I acknowledge the support from Jülich Supercomputing Centre, RWTH Aachen University, and Umeå University in Sweden for this research. Thank you. Bernd, I don't hear you.
Okay, thank you very much, Aravind, for this interesting talk with all these interesting details. Sounds like a very interesting new method, doing the analysis graph-based. And you showed already kind of two applications, one with a numerical algebra and now with I/O. Okay, does anyone in the participants have a question for Aravind?
I might have one question if I'm
Yeah, sure, go ahead.
the only one. So I did a couple of years ago, I did try something similar to trace IOs using various tools and to check how the IO pattern of applications look like. Like, is it random IO? Is it like interleaved IO and these kind of things? And what I found to be annoying about STrace is that it really impacts the performance of your application, and by that also reducing the I/O you might see because it's slowing down the computation and all these kind of things. Did you consider other tools compared to STrace?
I want this tool to complement the tools that are already available. So if it is for 24/7 monitoring, if you want to monitor the full application, I would probably go with Darshan. But this tool is for cases where, okay, you want to run the whole thing for just a few seconds. So this is a transformer model that I run, but I didn't do the whole training. So I just measured it for a few iterations. So it just ran for a few 10 minutes at most, and then I get this information. So yes, there is going to be a performance overhead, and this tool is not for monitoring full application. So once you start with Darshan or other tools, and then you see, okay, this could be an issue, and now you want to look into a little bit more detail, and then you come here. So this is for a second level of audit.
Okay, I see. And did you ever consider using System Tab? Because my experience with the System Tab was that it's like close to the real performance, and you also get all sorts of information, and even down to every single I/O and operation you can do.
No, I haven't looked into this tool yet. Maybe I would. Thanks for mentioning this.
Okay, thanks.
Thank you, Bjorn. Any other questions?
I do have one.
Sure.
From the screen that you showed here, of course, for this specific example, you're basing the efficiency of the reference performance of SGEM of 99 gigaflops per second, and then you compare it with the mean performance of 29.61 gigaflops per second. Is this generalizable enough to all kinds of application, or this is only just a mock-up for this example?
So the reason I call this lab linear algebra aware benchmark is that there is an implicit assumption that I know the flops of the application that is that I'm dealing with. So since this is a PIT model, I know. So I don't want to know the exact number of flops, but I need to have some value that is acting as a reference. So yes, if you want to generalize this to other applications, I would first break down the code and then try to identify the number of flops. Because once you map an expression or so let's say I'm looking at one particular iteration and I know these are the linear algebra calls, and for these calls I know this many flops. So I get this number. So that is a prerequisite. So what happens if I don't have this number? Then I could use, then it is not a lab report anymore. Then I would use the numbers from Liquid perhaps. Then it's even more generalizable than what you see here. But then again, the downside is Liquid is not available in all systems. For example, in HPC 2N in Sweden, the Liquid is not, those performance events are not accessible to you, so they have the highest paranoid level. And again, at that point, you need more. So also when you need something to be activated from the admin side. So when you don't have them, you can do something like this.
So would it be a consideration in the future that the user put in what the expected performance is on the reference side, or will this remain just an interesting artifact?
At the moment, I don't. So I see that this as a tool for supporters, not the user use this themselves. So if someone comes to you, or you as a supporter or a consultant, then you need methods to investigate their code. So as a supporter, you could do this.
Yeah.
And so this is for a tool for consultants and supporter at the moment.
I'm just thinking that because we as a supporter might not also know exactly what the code is doing at a specific time point. And therefore, assuming that the code should be crunching this amount of number, I think it's a bit too far-reaching.
Well, what you said is true, but this was the problem that we exactly try to solve. So linear algebra acts as a connecting language between the application. So you're not, the idea is to not to look inside the code. Look at the application, look, you know, the equations and get the flop. So here for this code, I did not actually look into the code. I did not care what transformer was doing. I did not care what PyTorch was doing, but I know the math. Then I know the flops. And then I just use these information to generate as much value as possible. So in that sense, I don't see this as something far reaching. It's doable if you know the math. Because the idea also is to not to look inside the code.
Yeah, I'm just thinking, yes, you do know the math of, let's say, the matrix operation, but you do not know if the application is supposed to do the intensity of the operation or the nature of the same operation that you compare it against. So that's my only concern. Yeah.
So here, what's a reference number, right? So it depends on what we want to analyze. So here, we are really not trying to optimize the performance, so not trying to squeeze the last bit. So if that is the case, then you need very accurate numbers. But here you want a reference, a benchmark. So there is a case. So GEM was run by myself. So this is a reference for this specific lab report. So this works for this setting. So if you're going to use this number to compare with something else, then you might need a different value.
All right, thank you. I do have a other smaller question, if you don't mind.
Yeah, sure.
I did notice that at the end of the slides, you mentioned that it's one log file per node, but in the earlier slides, you did mention that the STrace files are generated per process. Now, have you thought of, can you share about how do you manage the amount of inode if you're running in a very, let's say, exascale type of computation with thousands and thousands of processes?
That's a good question. Thank you. So version 1.0 of STrace initially generated one trace file per process. And then in the latest version, 1.1, I changed this to one file per node. So yes, if you're going to use one file per process, there is going to be a lot of overheads when you're running a job on 6,000 nodes and then on all the cores. So that is going to be infeasible. So this was the reason I changed it to one file per node. But changing this is not, yeah, true. So you just take this $$ off and then they all write to the same node and then they are differentiated by the PIDs here.
Right. Okay. Thank you.
Thanks.
Okay. Do you have any final question from the audience? It looks like not. So thanks everyone for joining. I hope you enjoyed the talk. The recording will be available soon. I will send, you will get an email once it's available and where it's available. So thanks everyone for joining and have a good rest of the day. Thank you.
Thank you.
Thanks
Bye.
a lot. Bye-bye.